Welcome to part 1 of the CipherVibe Cloud Security Capabilities series. This episode explains Platform Foundation, why it matters, how the capability works, which mistakes weaken it, and how to build it in a measurable way. A platform foundation is the shared control plane that turns disconnected security tools and telemetry into one governed operating system. Its value comes from consistent asset identity, normalized evidence, policy ownership, access control, workflow state, and trustworthy platform services. The key idea is that a security capability is more than a product feature or a collection of alerts. It combines people, process, technology, decision rights, evidence, and continuous improvement. We will examine its architecture, operating workflow, failure modes, defensive controls, implementation roadmap, and useful metrics. Coverage is not the same as effectiveness. A dashboard can show thousands of checks while the capability still fails because evidence is stale, ownership is missing, or remediation is never verified. The business outcome should be explicit. Teams need to know which loss scenarios the capability reduces, which systems are in scope, and which remaining risks require a conscious decision. To understand Platform Foundation, start with its architecture and vocabulary. The capability should create a traceable chain from source evidence to a security decision and then to an accountable action. First, a unified asset model assigns durable identities to accounts, workloads, applications, users, data stores, repositories, and findings. Second, ingestion services collect provider APIs, event streams, scanners, agents, and business context while preserving source timestamps and provenance. Third, a policy engine evaluates evidence consistently, supports exceptions with owners and expiry dates, and separates detection logic from presentation. Fourth, platform services provide tenancy, role-based access, audit history, search, reporting, notifications, retention, and reliable application interfaces. These concepts need shared identity, timestamps, provenance, ownership, and access control. Every summarized risk should link back to its source evidence and disclose missing information. A sound architecture separates collection, normalization, analysis, policy, workflow, and presentation. Teams can then test freshness, identity resolution, policy results, owner routing, and closure independently. Design for degraded conditions. Providers impose rate limits, schemas change, credentials expire, and events arrive late. A professional capability reports uncertainty and health instead of presenting incomplete information as fact. Trust boundaries deserve equal attention. Identify where data crosses accounts, tenants, regions, vendors, privilege levels, and administrative domains, then apply authentication, authorization, validation, encryption, and audit controls at those boundaries. A useful operating model for Platform Foundation follows a repeatable evidence lifecycle. First, discover assets and identities from authoritative systems, then reconcile duplicates before findings are attached. Second, normalize evidence into stable schemas without erasing provider-specific details investigators may later need. Third, evaluate policies, enrich results with ownership and business criticality, and calculate priority using transparent factors. Fourth, route work to the accountable team, preserve state changes, and verify closure using fresh technical evidence. Fifth, measure platform health through ingestion freshness, coverage, data quality, policy latency, and workflow completion. The workflow does not end when a ticket closes or an API returns success. Security closure requires fresh evidence showing that the risky condition is gone and does not immediately recur. Ownership should be established before urgent findings arrive using service catalogs, business applications, on-call schedules, and escalation paths. Prioritization should explain the influence of exploitation, reachability, privilege, data, business criticality, compensating controls, and confidence. Repeated findings should drive changes to secure templates, defaults, libraries, identity patterns, and architecture standards. Define escalation points for missing owners, disputed priority, failed changes, and evidence that suggests active compromise. Those conditions should move into incident or risk governance rather than remaining indefinitely in a routine queue. The fastest way to evaluate platform foundation is to study how the capability can fail. First, duplicate assets create contradictory findings and make executives distrust every dashboard. Second, stale connectors silently produce false confidence when data freshness is not visible. Third, overly broad administrative roles weaken separation of duties and expose sensitive cross-tenant information. Fourth, a proprietary data model without export paths creates operational lock-in and slows incident response. Fifth, uncontrolled policy changes cause alert spikes, broken metrics, and inconsistent risk decisions. These failures share a pattern. A local measure looks successful while the full outcome is weak. A connector, scanner, or repair can report success while coverage, exploitability, or recurrence remains unresolved. Measure whether the program improves important coverage, shortens exposure time, removes attack paths, and prevents recurrence, not how many alerts it produces. Exceptions need a reason, owner, compensating controls, approval, and expiry. Automation should reflect confidence, reversibility, blast radius, and business impact. Test both through controlled failure exercises. Correlate weaknesses instead of reviewing them separately. A moderate configuration issue, broad identity grant, exposed service, and sensitive data store may combine into a severe path even when no individual alert looks critical. A dependable platform foundation program uses defense in depth. No single scanner, policy, gateway, or agent should be expected to carry the entire outcome. First, define asset identity rules, authoritative sources, schema ownership, and reconciliation testing. Second, monitor connector permissions, failures, rate limits, ingestion lag, and last success timestamps. Third, use least privilege roles, service identities, approval workflows, immutable audit logs, and strong tenant isolation. Fourth, version policies as code, test changes against representative data, and maintain exception governance. Fifth, publish supported APIs, event contracts, export mechanisms, recovery objectives, and service-level indicators. Control design should include preventive, detective, responsive, and recovery layers. Together they establish safe defaults, identify drift, govern containment, and restore service. Least privilege applies to connectors, agents, orchestration identities, data stores, and administrators. Scope, separate, monitor, rotate, and test their access. Every control needs an owner and test strategy. Validate it with representative assets, negative cases, simulated attacks, provider failures, and rollback exercises. Integrate controls with engineering through clear pull requests, owner routing, reusable fixes, documented standards, and fast feedback. Preserve an evidence trail from detection through decision, approval, change, and verification. That lineage supports investigations, audits, lessons learned, and fair performance measurement without forcing teams to reconstruct history from separate systems. A practical implementation roadmap for platform foundation should build trust before scale. First, start with the asset model and 2 high-value data sources rather than connecting everything at once. Second, prove freshness, identity quality, access boundaries, and ownership before adding advanced analytics. Third, introduce policy versioning and exception workflows, then connect ticketing and response systems. Fourth, run failure exercises for stale data, broken connectors, excessive privileges, and regional outages. Fifth, expand only when teams can explain how evidence becomes prioritized and verified work. The roadmap is incremental because a focused production scope lets teams validate evidence, ownership, workflow, and control safety before scaling. Useful measures include asset reconciliation rate, connector freshness, policy evaluation latency, privileged role count, and verified remediation time. Give every metric a precise definition, data source, owner, and known limitation. Pair lagging indicators such as exposure age with leading indicators such as coverage, control health, exception expiry, and secure template adoption. Maturity means the organization can discover important risk, explain it, assign it, act safely, verify the result, and learn from recurrence. Review the roadmap quarterly. Changes in architecture, threat activity, regulation, business strategy, and provider services can alter both priorities and assumptions. Retire metrics and controls that no longer guide useful decisions. For more cybersecurity market intelligence, research, and educational briefings, visit CipherVibe.com. CipherVibe is operated by Cloudsectech LLC. This video is general education, not legal, compliance, financial, or incident response advice. Never access or test systems without explicit written authorization.